So ignoring all of those other things around it for now, we'll explain where they came from in a second. Things of form a plus b or x plus y or any two-term expression like that is what's called a binomial, where for this, we're going to look at how we can take values like that, binomial terms, and raise them to general powers n. And we'll end up with something like this, which for now I'm sure looks terribly intimidating to you, because it still looks kind of intimidating to me, to be honest. But we're going to see here that some nice patterns emerge when we talk about these powers. So, for example, when we look at something of form a plus b squared, that is a plus b raised to the power 2, well, it's something we should have some familiarity with. That's a squared plus 2ab plus b squared. It's pretty straightforward. You've done this many times. And what we can do here is take this kind of pattern and expand it, where work into this kind of field is often attributed to Blaise Pascal from the 17th century in terms of a certain triangle that you may have familiarity with, but interestingly, it actually predates him a fair amount, as there's evidence of similar work being done in China hundreds of years earlier. Anyway, what we can do here is think about what happens if we take those values n further and further out, where if we take it to some general power n there, we have a plus b raised to the power n is going to be equal to n choose 0 times a to the n plus n choose 1 times a to the n minus 1b plus n choose 2 a to the n minus 2b squared plus n choose 3 a to the n minus 3b cubed plus a whole bunch of other things with a similar type of terminology all the way up to n choose n times b raised to the power n, where again, remember n choose 0 and n choose n, even though we're including them in there for the sake of notation, they're both just 1. But that's a lot of additions. That's a lot of additions with a specific pattern. And that's where we get something like this. That's what we use summation notation for, is to be able to condense that all down and say that that is the sum from r equals 0 up to n of n choose r times a to the n minus r times b raised to the power r. And this is what's called the binomial theorem. It says that if we have terms a and b in there, and then appropriately defined n, where here we're generally saying n at least 1, n is a natural number, we get a sum of that form to describe the binomial expansion, where we can prove this type of thing using induction. It's a pretty complex induction proof, so I'm not going to expect you guys to know how to follow along with that. I'm not going to put it up here except maybe as like a quick bit so you can see what it looks like, but I think it's a little bit more intuitive, or at the very least a little easier to understand if we think about this in terms of that choice idea, in terms of those combinations, where we can think about those binomial coefficients, those n choose r type terms, as telling us how many ways we want to select our a's and b's, where because of the way that we're taking these things raised to the power n, every single term in that expansion is going to have a total of n terms, where some of them come from a and some of them come from b in terms of its factors. So, if we're starting from that an term, it's all an's. We can either think of that as being n choose n a's, or if we want to go with the notation they have there, n choose 0 b's. And that's how we can identify what that coefficient tells us, is the number of ways we select either a or b, where if we're going from an down, like we do with the way it's written there, we can see that our second term, in some sense, tells us that we have n minus 1 a's in there, and then we have n choose 1 ways to pick that single value b that's left over. And then going all the way to the far end, we're not taking any a's, so we have n choose n ways to get all of our b's. That is, we have one way to get only b's with n things, and you understand that. And if you're going to get something in the middle, something like the fifth term halfway down there, however far it is down there, you can do this for any number of powers. 5 might not be very far at all. N minus 4 of the factors inside of our expansion at that point are going to be a's. So we'll have a to the n minus 4, while the remaining of them, n minus 4, choose 4, because you've got 4 left over, will have to be b. And since they're all just b's, we don't care about the organization of them. They're just a collection of the same thing, which is why we are choosing them, as it were. It's why order is irrelevant, so we get to use the binomial coefficient to be sure. And there's also ways we can think about this geometrically. This isn't a unique or unexplored field after hundreds of years, but that should give us some basic intuition for how this pattern came to be. And the next thing we're going to see here is how we can use it first to draw out an entire expansion, and then to identify specific terms within expansions.